Welcome to our 10th lesson on wave, sound and light. As we said, today we're going to be looking at the nature of electromagnetic waves. Now our electromagnetic waves have got two types of properties. One which is the wave properties and the other one known as particle properties. Now we do know that electromagnetic waves have got wave properties because it also interacts in the following way that waves does. It's got reflection. That means that it can go and bounce off objects like in an echo's case. It's got refraction. And refraction you will do a bit later again in detail, but refraction is all about the bending of the waves the moment that it changes direction from one medium to another. Now just to give you an indication, if you're standing on land and you're shouting upwards, you've got colder air though closer to the bottom, and maybe you've got warmer air at another level at the top of your atmosphere, then there will be bending of light waves because this is two different type of mediums in which this wave will going to travel through. So the moment that your wave sound gets shouted out, it would not just continue straight through. Because this air is warmer, that means less dense, it's going to bend more upwards, which means it's going to bend, in this case, in the following fashion. Now do note we will be doing refraction, but later this is just to give you an indication so long of what refraction actually is. So electromagnetic waves can undergo wave properties because it's got reflection, refraction, and the last one that it also in this case is the same as wave properties is interference. Now interference again, remember, is when we had waves meeting each other and undergoing superposition. Now a quick example of superposition again is if I have two waves that's going to meet each other in the same medium. In this case it will be constructive interference because they will form a higher amplitude, but it could also be destructive interference where they'll form a lower amplitude if they're coming from different directions of the rest position. So electromagnetic waves can undergo reflection, refraction and interference. Now we do know that it's got particle properties as well because that's evident during collisions with other materials. Now we will look in a bit more detail closer to the last lessons on electromagnetic waves as going to the particle properties. So first off, we're going to look again at the wave properties and then we'll later go over to the particle properties. Also, unlike sound waves though, electromagnetic waves doesn't need a medium to travel in. Now if you can remember out of our previous lessons, we created a situation where there was a vacuum, and a vacuum means we've pumped out all the air particles, and then we realized that if we do have a bell on the inside of my apparatus where there is now a vacuum, we won't be able to hear the sound because sound needs particles to transfer its energy. But electromagnetic waves doesn't need any particles to transfer its, in this case, its energy. So therefore, it can be transferred within a vacuum. Now we're going to be looking at the generation of electromagnetic waves. Note though that in many cases I'm going to abbreviate electromagnetic waves with EM. Now during the generation of electromagnetic waves, we are going to refer to a few terminology and as well detail on charges, which you will only learn a bit later on again. So we're just going to first briefly go over to the generation of electromagnetic waves. As I said, you might not completely understand in detail because some of those concepts will be discussed later on again. Now electromagnetic waves will arise when accelerating charges, and when we talk about charges we basically refer to negative charges, and they induce a magnetic field. Now whenever you do have charges that's moving from one point to another, and that's typical of our overhead power lines that we see alongside the road that transports our electricity from the substations to our homes. Those specific power lines have got accelerating charges within them, and that's then transporting our electricity, and that induces a magnetic field surrounding these high power lines. Now note that magnetic fields is not visible, it is imaginary lines surrounding these specific charges. Now because the movement of these charges continually changes, so the magnetic field will also continuously change. because the magnetic field is dependent on the direction of the charges. So the moment that they change direction, then the magnetic field will also change its direction. Now, something else that the magnetic field also does is it's going to induce an electric field. And this induced electric field is always perpendicular to the magnetic field. Now let us go and see this on a graph. Unfortunately, this is though a three-dimensional type of movement, so we're going to, in our best way, try to explain this on a flat sheet, which is then what you'll see as your screen in the front. Now before drawing them, let's just take into consideration that our electromagnetic waves, now note though that we've said our changing charges induces a magnetic field, and this magnetic field induces an electric field. So this is where the electromagnetic waves in word comes from. Okay, so as I said, it induces an electric and magnetic field, and these fields are perpendicular to each other, but they're also perpendicular to the movement of the wave. Now, if you can remember, we said previously, waves that are perpendicular displacement waves to the movement is thus known as transverse waves. So we're going to be seeing our electromagnetic waves as transverse waves. But in this case, there is two waves that it's made up of. It's made up of an electric field and a magnetic field, and these two are always 90 degrees to each other and 90 degrees to the movement. So let's start off by drawing our electric field in this case. So electric field's displacement is 90 degrees to the motion. That is what perpendicular refers to. And we would then note that 90 degrees to this, we will then have the magnetic waves. Now that means at right angles, which is 90 degrees to the electric waves, we're going to have our magnetic waves, and they're basically pointing towards you on a flat line. And they're pointing 180 degrees away from you. So this is how our electromagnetic waves will oscillate. And oscillation just means how the waves will then move in our wave patterns. Now the short question which I would like you to go and attempt is first give two properties of electromagnetic waves that gives it an indication that it is a wave, and what type of waves are electromagnetic waves made up of. Remember to first pause your play and attempt the question before you're going to be looking at the answer. Now there's basically three properties that indicates to us that electromagnetic waves are indeed waves, and that is because of reflection, refraction, and interference. Now you could have mentioned any two of these three. Now when we go over to the next question, it asks you what type of waves does electromagnetic waves consist of. Now here is our electromagnetic waves again, and it's made up of electric waves and magnetic waves, just as the name says. Now in the next lesson, we're going to be looking at the electromagnetic spectrum and how we can go and do calculations from our electromagnetic spectrum.